This section is on the Doppler effect. The Doppler effect has to do with how sound or light waves are perceived when the source and observer are moving relative to one another. We've all seen a situation where a fire truck or some vehicle with a siren is approaching us, and so in this picture we would be over here where this observer is. And when it's approaching us, we'll hear a higher pitched sound, ee, and then as the vehicle goes by, the sound will decrease in frequency or pitch. That's the Doppler effect. What's happening is that as the source is approaching us over here, the source is going this way, kind of approaching us. Here's our little observer here. The waves in the forward direction get bunched together, and we perceive that as a higher frequency because short wavelength corresponds to a higher frequency for us. Similarly, in the backward direction, the waves get stretched out. And so we see a longer wavelength in the backward direction. So if we were listening over here, as the waves got towards us, we would see a longer wavelength or a lower frequency, a lower pitch in the backward direction. And so if the source is approaching us, we hear a higher frequency. If the source is receding from us, we hear a lower frequency. The same is true if the source is stationary and we're moving towards the source, and we'll talk about that in a little bit as well. The Doppler effect has several applications. Actually, it has very many applications, but a few that you might be familiar with. One is in police radar detectors. A policeman or a highway patrolman will sit with a radar detector and a radar gun, and the radar gun bounces a signal off your car, and that signal comes back with a Doppler shift on it because the car it bounced off of was moving. And so the highway patrolman will measure a higher frequency for an approaching car than the signal he sent out. And the difference between those two allows the highway patrolman to determine the velocity of your car. Same thing if the car is moving away, they would see a lower frequency returning, bounced off the moving car. And that would allow them to calculate the velocity of your car as it's moving away from them. Another example is in astronomy, distant galaxies are moving away from our galaxy because the universe is expanding. We can measure the velocity of those distant galaxies by looking at specific wavelengths of hydrogen light and noticing that in distant galaxies those wavelengths are shifted. They're so-called red-shifted because the galaxies are moving away. And what Edwin Hubble noticed was that the farther away the galaxy is, the greater the shift. In other words, the greater the velocity. And so how fast distant galaxies are moving away from us is proportional to how far away they are. That's a picture of an expanding universe. If a train is stationary, if it's at rest, then it sends out sound waves in all directions, right, with the same wavelength. And so we get a wavelength in the backward direction that's the same as the wavelength in the forward direction. And so each observer in front of and behind the train hears the same frequency. This is different than what happened when the fire truck in the last picture was moving. So suppose a truck is stationary, right, and it's playing a siren with frequency Fs. We'll use Fs to represent the frequency of the source, right? That's what the S means. And that means when you're sitting in your truck, it's playing a particular frequency. You're not moving relative to it. It's just what comes out of your siren, right? Then we can look at our standard formula for the relationship between the velocity and the wavelength and the frequency, and we can say, look, the wavelength coming out of our source is VW over Fs. VW is the speed of the wave. That's the speed of sound, right? And remember, that only depends on the temperature, and usually we say it's approximately equal to 344 meters per second, right? Depending on the temperature. But so this allows us to calculate our wavelength, right? VW is the speed of sound. Lambda s is just the wavelength of the wave leaving our stationary source. Right? And so that's what goes out in the forward direction. Now we're going to look at what happens to this wave as seen by an observer if the source is moving. Again, the waves are going to get bunched up in front, and we're going to talk about how those waves get bunched up and what happens to the wavelength that's seen by the observer that we saw in the first slide. So this is a picture of our situation where my truck or my train, the thing that's producing the sound, is stationary. And it's just sending out waves in the forward direction, right, going this way, and it's sending out waves in the reverse direction, and they have the same wavelength. There's no bunching in the forward or bunching in the backward or stretching in the backward or stretching in the forward direction, because this truck is stationary. Right, now we're going to look at what happens when this truck is moving, like we saw before. So now we see that in the forward direction, once the truck is moving, right, in the forward direction with, say, speed, velocity of the source, right, once the truck is moving in this direction, then as it emits these waves in the forward direction, it's chasing after them, right? It's chasing the waves as it emits them, and so they're getting bunched up in the front direction. You can think of yourself as on a boat. The bow of the boat, the waves kind of get bunched up there. Whereas in the backward direction, it's leaving them behind because it's moving away from them, right, as it's emitting them. And so we get stretched wavelengths in the back and bunched wavelengths in the front. And so an observer over here sees a shorter wavelength than an observer back here. So we have a stationary source here, and it's playing its sound at this frequency. Right, Fs, whatever we call that, 300 hertz or something like that. And so it's emitting these waves, right? And the wavelength, this is, say, each one of these lines, say, represents a peak, right? Then the wavelength is the distance between the peaks, and we call that lambda s. If the frequency is Fs, the frequency is just 1 over the period, which is Ts, and so if we know the frequency, we know the period, and the period is the time between the peaks. It's the time for one wave to go by. So now we have a moving source, right? Now our truck is traveling along at speed Vs. Up here, the truck was at rest, but now our truck is moving. And so just like before, it's playing this, this tone, this siren, which has a frequency of Fs. But as it emits the wave, it's chasing after the waves by traveling in this direction. So whereas this wave is moving along just as the one above it is, before the next wave gets released by the truck's siren, the truck has moved forward by a certain amount. How much? The speed of the truck times the period of the wave. The period of the wave is the time between this peak and this peak. That's how much time elapses between when the siren puts out one wave peak and the next wave peak, and during that time the truck has moved by this distance. And so instead of having a full wave lambda s like we did with a stationary truck, our new wavelength is lambda s minus how far the truck moved. And so we get a bunched up wave in front that has this wavelength, which we'll call lambda O for the observer, right? And we get lambda O is equal to lambda s minus the speed of the truck times the period of one wave. So now we're going to look at an observer in front of that approaching sound source. That's somebody standing ahead of the truck or the fire truck on the previous page. And we're going to look at what their observed frequency is. Now they've got a sound wave approaching them at the speed of sound, and so that's VW is about 344 meters per second, and it has a wavelength of lambda naught, whatever that bunched up wavelength is, right? So the frequency an observer hears is the speed of sound, just from our regular V equals lambda times the frequency equation. The frequency, if we solve for the frequency, we get the speed of the wave divided by the wavelength. But now we've got this bunched up wavelength, and so we evaluate that here. Here's our bunched up wavelength. It's the wavelength that would be coming out of the source minus how far the truck moves, velocity times time for the truck, for the time of one wave, right? The time of one wave way over here is just 1 over the frequency. That's the period. And so that's the time we put over here. Similarly, the wavelength for the source is what we said on the previous page. It's just the velocity of the wave, the speed of the sound, again, 344 meters per second, in air divided by the frequency of the source, again. And so this wavelength observed, instead of looking like this, now looks like this. It's velocity of the wave divided by the frequency of the source minus the velocity of the approaching truck divided by the frequency of the source. And so we can take this and plug it in here, and we get this equation here, right? It's the velocity of the wave from way up here, where we defined our observed frequency, divided by velocity of the wave over the frequency of the source minus velocity of the source over the frequency of the source. And if we rearrange, we get this. The frequency observed is equal to the frequency of the source times the velocity of the wave divided by the velocity of the wave minus the velocity of the source. And so you can look at this equation and say, well, what happens if the source isn't moving? Right? If the source isn't moving, we would expect the observer to hear the same sound as being played by the source. And that's exactly what happens. If I stick in Vs equals 0, I get Vw over Vw. Those two cancel, and I get right back to my source frequency. If this number is a positive value, like 10 meters per second, or 20 meters per second, or 30 meters per second, and the sound is approaching, then instead of being 344 meters per second in the denominator, this is something smaller, maybe 334 or 324 if this is 10 or 20. This number becomes greater than 1, and the observed frequency is a higher frequency than is being played. We hear a higher pitch from our observed frequency. Similarly, if the source is receding, this sign, the velocity of the source is negative. The negative and the negative would make that a positive. The denominator would be larger than this numerator, and we would get a reduced observed source. So we'll look at an example now. So here's a simple example. An ambulance with a siren playing a tone of 300 hertz is traveling at 30 meters per second towards a stationary observer. This is just sort of what we've been talking about over the last few pages. What frequency does the observer hear? Right? Then we're looking for this frequency. Well, here's our formula. We just have the frequency of the source, which is 300 meters per second, times the velocity of the wave, divided by the velocity of the wave minus the velocity of the source. And so we just plug in all those numbers here, and we get the frequency heard by the observer is 329 meters hertz, which is a higher pitch, corresponds to a higher pitch than the 300 hertz that the siren is playing. So for the case of the source receding from a stationary observer, right, the frequency formula becomes this. Instead of a minus sign here like I had before, there's a plus sign, and we won't rederive it for this, but this is a formula for a receding source where we're just going to plug in the positive speed here and have a plus sign between the speed of the wave and the speed of the source. And so for the ambulance problem on the previous page, let's determine the frequency heard by the observer after the ambulance went past. So now the ambulance is going away from the observer. And so we use this formula. And once again, we just have to plug in our observed frequency is equal to the frequency at the source times the speed of the wave divided by the speed of the wave plus the speed of the source. And we plug in here and we get 276 hertz, which is a lower pitch than we heard than the stationary observer would hear, which is 300 hertz, or that an observer who is being approached by the ambulance would hear, which we saw on the previous page, was 329 hertz. So what about the case when the source is stationary? Now my ambulance or fire truck isn't moving, but the observer is moving. So say the stationary ambulance is playing its siren, and an observer is approaching at this speed v observer, right? This is my little observer here running towards the sound source. As you might imagine, this person passes through the waves faster than someone who would be standing still would. And so they're going to hear a higher pitch. And so for an approaching observer, we get this formula, which we can derive very similar to the way we did it for the stationary observer and moving source, but we won't. We'll just write the equation down. Similarly, for a receding observer, the observed frequency is the speed of the wave minus the speed of the observer divided by the speed of the wave. A tornado siren is playing a 400 Hz tone. What frequency does a driver traveling at 30 meters per second hear when she is approaching or receding from the siren? And so we just grab the formulas on the previous page and say for an approaching observer, the frequency the observer hears at a stationary source is the frequency of the source times the sum of the speed of the wave plus the speed of the source divided by the speed of the wave. And so for an approaching observer, we get 435 Hertz. Similarly, if the observer is receding, we just get a minus sign here where we had a plus sign. And so we get a frequency observed if the driver is driving away from the tornado siren by just solving the same equation is 365 Hertz. In the first case, where we're approaching, the driver is going through the waves faster than they would be if she were standing still and the waves were coming at her, because she's driving towards them. So she sees more waves per second, and so she hears a higher frequency. Similarly, if she's going away, she's going through the waves slower because she's driving away from them as they're approaching her, and so she hears a lower frequency. So now we can combine our multiple equations into a single one in which we get the frequency heard by the observer in terms of the frequency of the source, the velocity of the wave, the speed of the wave, in our case usually the speed of sound, and then the velocity of the observer and the velocity of the source. This example, or this equation, allows us to have both a moving observer and a moving source. In this equation, the top signs, the plus in the numerator and the minus in the denominator, are for when the source is approaching the observer or the observer is approaching the source. Similarly, the bottom signs are if they're moving away. So imagine if we had a police car, say, right, chasing a bank robber or something like that, right? And we want to know what frequency the observer hears, right? Well, here's the siren, and it's putting out the waves. And so if we want to know the frequency of the observer in this case, we can use this equation and say, well, these are the velocity of waves, both are the speed of sound, right? In this case, the observer is receding from the source. That is to say, the observer is running away from the source, and so we would use the bottom sign in the numerator because the observer is receding. Similarly, because the source is approaching the observer, we would use the top sign in the denominator, and so we would have VW minus V observer over VW plus V source in this example.